In this video, we will talk about the trends in the periodic table with regards to the atomic radius. So the atomic radius just simply is the size of the atom. So imagine the atom is a big circle or a big sphere. We take the radius of that and we'll get the atomic radius. So this is different than the ionic radius. The atomic radius is just for neutral elements in the periodic table. So what is the relationship? Well, the relationship is a little bit counter to what we would normally think for the other trends, namely ionization energy and effective nuclear charge. So elements on this side of the periodic table, on this side of the ledger, the alkaline metals and the alkaline earth metals, you have to recognize that they like to be +1 and +2. We have one valence electron here that's sort of out there. It's outer, and it's out there because you see, once that outer electron is gone, these guys, particularly group 1, become noble. They achieve the electron configuration of a noble gas, and so they achieve quote-unquote nobility. Same thing with the alkaline earth metals. You see, if magnesium or beryllium or calcium lose 2 electrons, they become noble and achieve the nearest electron configuration of their nearest noble gas. So having said that, these electrons, the +1 and the +2 state, are very outer. They're almost out there begging some element, usually it's these guys over here, they're usually begging some element to come in and take those outer electrons. So that's why these are generally considered much larger in terms of the atomic radius. Now contrast that in the periodic table to the situation over here. These guys, particularly the halogens and then group 6A or 16, they like to be -1 and -2 respectively. These tend to, they're very what we call electronegative elements. They want to sequester, they want to grab. They have a strong affinity towards electrons, natural affinity, natural drawing power and suction power towards electrons, particularly those in the p orbital. S orbitals are a little bit more outer, ready to give, ready to bond if it's a covalent molecule. P orbitals are a little bit more held tightly together. Obviously the noble gases, this region, it's a completely filled electron shell, completely filled orbital, completely filled energy level 2, completely filled energy level 3, completely filled energy level 4, so on and so forth. So this area here would like to sort of grab onto their electrons, particularly as we'll learn later in Lewis structures. These halogens here are very electronegative, so it's not even a fair fight. They grab and have a high affinity for electrons. Because of that drawing in power, the atomic radius actually has this sort of trend in which as you go this way, that is to say from right to left in the periodic table, the atomic radius increases. So you're getting larger and larger atoms as you go down across the periodic table, as you go across the period this way, right to left, and going up and down the group of a periodic table, the atomic radius also increases. Okay, so we have an increase going from right to left, and we have an increase going down the group. So increasing atomic radius going down the group is very easy because you see here, this is principal quantum number 1, n equals 1. Here the second row has energy level 2, energy level 3, energy level 4. The period, as the period increases, you're getting more and more and more and more and more outer. And the more and more and more outer you go, the more and more outer electrons you have. Look at cesium. Also, obviously, the larger and larger the atomic radius becomes. So it's very simple here. The explanation as to why the atomic radius is larger as you go down the group of the periodic table just means simply because we have a larger principal quantum number, more energy levels. The reason why the atomic radius increases from right to left across a period and it increases down. The reason why it increases across a period simply because the s electrons here, they like to lose electrons to attain noble gas status. Now looking at the transition metals, it's really iffy, right? The transition metal series, the atomic radius is not something that has a very specific trend. We know these love to be +1 and +2. We know these love to be -1, -2, because that's how you achieve noble gas status. The transition metals, the atomic radius generally follows that same trend that is shown here, but you can definitely see some exceptions. Finally, we want to mention the ionic radius. So the ionic radius, if you're an anion around here in the periodic table, as an ion, you gain those electrons, you gain those electron clouds, you tend to be larger. So anions are larger. We're talking about ionic radius, not atomic radius. And then here in the periodic table, when we're talking about cations, okay, the +1, +2, obviously if you're +1 and lose an electron, you lose the associated electron density, you lose the associated electron cloud, you're also going to be smaller. So cations are going to be smaller by virtue of sacrificing their electron density. Anions are going to be larger by virtue of gaining electron density. The overall trend in the periodic table then for atomic radius, not ionic, atomic radius, is that it increases from right to left across a period, and it increases down a group because of increasing principal quantum number.